Okay, so this is the last talk of the day, and boldly standing between all of you and coffee, we have Theo O'Neill, who will be talking to us about the topology of the local disk halo interface.
All right, well, thank you for that comment. And hi, everyone. So I'm Theo O'Neill. I'm a second-year PhD student here at the CFA, and I actually mainly work on ISM science in our own solar neighborhood. So what I'll be talking about today is a new method that I've been working on developing to characterize the topology of very local structures in our own solar neighborhood that may be contributing to the disk halo interface relevant to the CGM. And so as just a brief overview of what this talk will really focus on, I'm interested in characterizing the sort of structures that might be contributing to a galactic fountain flow. This sort of process, as a quick refresher, is summarized in this schematic cartoon over on the left. But so in the disk of a galaxy, we have clustered supernovae, which can carve out voids in the interstellar medium, known as bubbles or superbubbles. These tend to range from tens to hundreds of parsecs in diameters and are basically ubiquitous throughout the disks of galaxies, as I think is shown really nicely in this recent JDA-T result of another external galaxy. If these bubbles and voids can expand to a sufficient size such that they reach the scale height of gas in a galaxy, they can burst out of the disk and form what we call a chimney into the lower halo. So where they vent hot enriched gas into the halo, which can cool and fall back down onto the disk in a returning galactic fountain flow. These bubbles and chimneys are so common that our own sun actually happens to be in the center of a bubble. It's very creatively called the local bubble. We've known about it for 50 years, but our recent work has suggested that this bubble may have formed an asymmetric chimney into the galactic northern hemisphere. That's that big low-density purple region up on the top there. You can check out our recent paper for more on that work. Results like this one, where we're considering very local bubbles and chimneys, have been enabled by a real revolution in ISM science over the last decade, which is the development of the field of 3D dust mapping. An example of such a map of 3D dust extinction within 1.2 kiloparsecs of the sun is shown here in the center, created by Gordian Edenhofer et al. Earlier this year using Gaia XP data. Maps like these are made by inverting extinctions to stars with known distances in order to statistically reconstruct where dust clouds are likely to fall along the line of sight. This map in particular I'm really excited about. It achieves parsec resolution up to 1.2 kiloparsecs off the plane at a maximum distance. So for the first time, we can really start to constrain the very local extraplanar clouds of dust and gas in our own solar neighborhood and start to investigate what sort of bubbles and chimneys and clouds may be a part of this very local disk halo interface. And what we need for really analyzing data sets like these, which are rich and full of substructure, is statistically rigorous and robust methods for characterizing structure across all scales. And so what I will argue is that one such technique that is very well suited for this sort of analysis comes from the field of computational algebraic topology. It's called persistent homology. And this will be the briefest ever overview of this very complex field of math with no equations, and then we can move on to the results. Basically, this field, persistent homology, is concentrating on how we can identify voids or holes of different dimensions in a data set. A data set can be anything. In our case, it's a data cube, a 3D dust map. We can imagine that there's a variety of potential dimensions that a hole or void can take on in this data space. The easiest one that I think to think about is a two-dimensional void. You can picture a closed surface like a balloon with a low-density interior. Physically, this maps to something like a feedback-driven bubble. We can additionally consider a one-dimensional hole. This is, you can picture in your mind a rubber band which can stretch or deform, but is always making a closed loop. This physically is something like a ring or a tunnel connecting different feedback-driven bubbles. And finally, we have our zero-dimensional holes, which most of us non-mathematicians wouldn't really think of as holes at all. In a dust map, these are clusters of high-valued connected pixels, so things like clouds or filaments or spiral arms. This technique is very effective at identifying all sorts of different holes of these dimensions. One notation housekeeping announcement. Unfortunately, when mathematicians were naming these homology groups as H2, H1, H0, they were not thinking of astronomers. So throughout this talk, when I talk about H2 or H1, I'm not talking about hydrogen. I am talking about these homology groups. For this project, we apply this technique of persistent homology to this new 3D dust map created from Gaia XP data. A brief bit of advertising, this sort of analysis that we do is contained in a Python package that I'm currently developing called Perch. Stay tuned for the public release of that package in the near future. So if we consider solely the set of H0 voids in this 3D dust map, so again, this is our zero-dimensional voids, things like individual molecular clouds and filaments. What I'll show here in this video, our dust map is here in gray, and then in pink is different distinct layers in our hierarchical segmentation of this data set being toggled on. There's a lot of structure here, which I won't really go into at all, except to say we pick out many distinct individual molecular clouds both in the disk and notably a lot well outside of the disk as well. I think it's revealing to look at the distribution of z heights. So in our Cartesian coordinate system, vertical towards galactic north and south, distance above the sun's position at z of 0. But to look at this distribution of z heights of these these clouds. The majority of these clouds are concentrated very near to local estimates for the galactic midplane at about -30 parsecs below the sun. This is a very broad distribution with quite heavy tails. 1 sigma interval here is about 250 parsecs. Notably, this seems to agree quite well with different estimates for scale heights of molecular gas and dust in external galaxies viewed edge-on. And so what we can do, because I'm an ISM scientist and not a CGM scientist, we can say that things that are outside of this interval, so a few hundred parsecs above and below our plane, are high altitude. If you're unhappy with something at 500 parsecs being high altitude, I don't know what to tell you. But when we look at this subset of high altitude clouds, which are highlighted here in pink, we really do see quite a large and distinct population of structure well above the disk of our own solar neighborhood. There's hundreds of clouds up to a kiloparsec above and below our disk. And interestingly, there's a pretty pronounced asymmetry in the numbers of clouds in the northern hemisphere versus the southern. At this 1 sigma interval, there's 1.5 times more clouds in our northern than southern hemisphere. If we go to the furthest extreme, so we do a 3 sigma interval here, there's 3 times more clouds in the north than south. This sort of asymmetry is kind of unexpected. If these clouds are being driven up out of the disk by a galactic fountain process, it's a bit odd that we would have had some sort of past asymmetry creating a present day imbalance in our high altitude cloud population. What it reminds me of is the known asymmetries in the distribution of intermediate velocity clouds in our sky. This is a well-known result where there's many more infalling IVCs in the northern hemisphere than in the south. So one application of this topological analysis is being led by my collaborators Andrew Sagery and Catherine Zucker. So we're matching our 3D structures identified with dust maps to IVCs viewed in the hydrogen and other tracers. So what I'm showing here are just a few IVCs which we've successfully detected in this 3D dust map. So we have, for the first time, we're able to compare the 2D and 3D morphologies of dust inside of these IVCs and compare them to their velocity integrated morphologies with hydrogen. Finally, we can additionally look at our populations of 2-dimensional voids in this space. So these are shown here in blue. The contrast isn't great. We can map these low-density 2D void interiors to their higher dimensional shells. In this video, the sun is in the center, and a variety of candidate voids of all shapes and sizes are shown on the exteriors here. We believe that many of these voids, identified topologically, are likely the result of recent feedback. I'm showing here a few well-known voids, the Orion-Eridanus superbubble and the Gum Nebula, identified with H alpha, which is a tracer of recent feedback. So we're detecting these voids in 3D for the first time, as well as a whole menagerie of other candidate voids, candidate bubbles, which can be explored using this method. Finally, we can consider things like the statistics of our 2-dimensional void candidate feedback-driven bubble population. We have a typical bubble size of about 30 parsecs in radius. There's a variety of scaling relations between void properties. Most notably, I'll just highlight the one on the right here. Larger voids tend to be preferentially extended vertically in the z direction out of the disk. This is exactly what we'd expect if we're constraining the evolution of feedback-driven bubbles, which start to expand preferentially vertically towards lower density materials out of the galactic disk. So really starting to potentially constrain some early stages of chimney formation, contributing to this high altitude material. And as a final plot here, we're showing, not very well in contrast at all, unfortunately, but a sample of 9 candidate chimneys identified using this method, which are two-dimensional voids which appear to be reaching out of this low-density disk material and starting to extend into the very lowest regimes of our disk halo interface. And again, we have an imbalance in the orientation of our chimneys in this space. We have many more chimneys oriented towards the galactic north than south, which is reminiscent of the same imbalance in high-altitude clouds in this map. So I'll leave up my takeaways, and then I'm happy to take any questions.
Yes, here.
I must have missed it. How do you get distances to these?
Yes, so the 3D dust mapping, I didn't have any part in creating this map, but the distance comes from this. These maps are created by taking a sample of billions of stars with known distances from Gaia and known extinctions, then you statistically invert over the full region of stars covered in order to make a 3D map of dust clouds' densities and distances. So it's from the construction of the 3D dust map.
Very nice talk. I wonder, so we know there is a galactic center chimneys, which corresponds to very hot plasma. For these chimney where you detect voids, are there corresponding X-ray structure related to this?
That's a fantastic question. I have not done that sort of analysis yet. It's something that I would really like to do. It would be very useful to constrain whether these bubbles are recently feedback driven, if they did in fact have these hot plasma interiors.
Okay.
You have a nearly complete, or somebody has a nearly complete map of stars in this whole region of the galaxy. So I wonder if you have the information you need to correlate the shape of the structures with the age of the cluster that produced them.
That's another great idea. That's something we should definitely look into. Some earlier work along these lines has been done by my collaborator, Catherine Zucker, so looking at the ages of young stellar clusters on the surface of the local bubble, which our own sun is inside of, in order to constrain its expansion in age. So yeah, it could absolutely, something similar could be done for this population.
It's back here.
Yeah, this north-south asymmetry is really interesting. You mentioned you see it in intermediate velocity clouds as well as these clouds. So what do you think is causing that? Like, why do we have this asymmetry?
I think it's very easy to speculate, and it's very hard to actually come up with the correct answer to this question, given the information. I think it really could be anything. Maybe 10 million years ago, some infalling event led to more stars forming slightly above the plane, and then now we have all these northern chimneys and high-altitude material. Maybe the work with the Milky Way is acting weirdly in some way. It's very hard to say. I would love to know the answer.
Okay. Yes.
Yeah, great talk, awesome visuals. I was wondering, from this image, it looks like local bubble is the largest nearby. Is this some selection effect, or?
This is an effect of the bad contrast on this projector. But so there's a very large bubble here in dark purple, which we can't see right now. This is called GSH 23800+09. Found by Carl Heilev in 1998, and so that is the actual largest void in this space. Yeah.
Time for one more question. Is one? Yes.
You flashed this JOST image of the external galaxy where they've also started to quantify like the bubble size distribution. So have you compared?
Yes, I recently joined the Things collaboration as a student affiliate who released that image. So I'm starting to do that sort of bubble size distribution myself, actually. So far, it looks similar. Of course, we do have projection effects. We can actually find things in 3D here, and in an external galaxy, we only have 2D. So you have to be a little careful, but so far, it does look similar.
Okay. Thanks. Let's thank the speaker again.